Hello and welcome. Um, so I thought I'd do some warm-up problems for admin of code in preparation for the contest starting here on uh, last day of November. So I'm probably going to do some streams. I think I'll stream today and maybe over the long weekends. It's a long weekend for people in the U.S. anyway, with Thanksgiving. Um, and I thought we could go over some previous year's problems. Um, and this also, I mean, this serves a dual purpose for me as well, which is I need to get up to speed. I think I'm going to try and be competitive this year, go for leaderboard positions. I'm by no means a competitive programmer. About the only thing that um, the only contest that I do in the year is admin of code. But we'll see. We'll see how it goes. So few things, some house cleaning. Yeah, I have a function here using um, the HTTP command library that comes with dialog, and we can use this to get the problem inputs, which is going to be useful from a speed perspective. I don't have to copy the input or save as or whatever. A lot of people that do admin of code have these type of functions. It's basically just we set a path for the file. If it exists, then we just read it. Otherwise, we try and download it. So um, actually, HTTP command is pretty good. I recommend taking a look at it if you're using dialog. Um, so yeah, I mean, I guess I'm recording this for YouTube as well. So I guess we will just get into some problems. I decided. Um, So out of all of the events that we have, I decided to do some problems from 2017. Now, as you can see, I solved some of these. I think I've sort of sporadically done problems from all of the years in admin of code, although not all of them in APL. I've used other programming languages and such. So, um, yeah, I mean, it's been a while since I looked at them, and I think this will be useful anyway, even if I've already collected the stars for these problems. And there are other years, 2016, yeah, I've only done a few. 2015, only the first three. This Christmas tree is pretty iconic from a advent of code perspective. Yeah, anyway, let's look at some problems. Okay, and right, so I laid the ground rules. We're going to go for speed. Basically, I'm going to try and solve the problems as quickly as I can. And that means the explanations are going to be somewhat minimal. I've already posted explanation videos for uh, the 2019 problems, so you can go to my YouTube page and check that out. Um, and I think what we'll do is after I actually get the answer, then we can sort of go back, explain how I arrived at it, format the code nicely, and I'm intending to set up a GitHub where I have solutions for all these previous year solutions that we go through. All right, so problem one. Problem one is usually pretty easy. Solving a CAPTCHA requires you to review a sequence of digits, your puzzle input. And okay, so yeah, I kind of tested my pget function on 2017-1. So the length of this is 1, so we're just dealing with one row. So we can assign this to p. And actually, because we're considering the digits individually, then we'll just do for each execute. Yeah. Okay. Oh, geez. Sum of all digits that match the next digit in the list. The list is circular, so the digit after the last digit is the first digit in the list. 122 produces a sum of 3. This produces 4 because each digit matches the next. Yep, so it is circular. Okay. And again, okay, great. Well, how long of a list are we talking here? 2136. So we'll neg1 take p, and append it on the beginning. And we'll call this pt, I guess. And then, so for each digit, if we want to check whether digits match the next, we do a windowed reduce. And this is going to be one less, so we have to put 0 on the end, right? Oh. No, that's right, because PT is going to have one more. So then we can use this as a Boolean vector to filter PT, sum that, 1253. Yeah. Okie doke. You notice a progress bar that jumps to 50% completion. Apparently, the door doesn't get satisfied. Halfway around the circular list. Okay, so how long is P? 2136. 1068, so we want a 1068 two-row matrix out of P. And then we'll assign this to PT now. And we're doing an equal reduce first, right? And we will use this against, I think, the first row of PT. So PT take, like so. This. And we're including both digits. Yeah, this produces 6 instead of 3, so this will have to be 2 times sum. 1278. Yeah. Okay. Great. Well, that's the first problem. First problem is generally pretty easy. So, yeah. See APL. This is 2017. 1 dialog. Yes, please. All right, so what are we doing here? This is, let me change CD here. And this is going to be nget in/1.txt1 row take beginning for each execute. That's our problem input. All right, this should work. What? Oh, right. Yeah, nget take. That's right. So this just needs a second one of these. Right. Okay, great. And then for problem 1, what was it we were doing? We neg1 take, it's this, right? This is part 1. And this is part 2, but we have to generalize this a little bit because it may not be 268. So this will be length P2 divided by 2 cons P row commute domain error. Oh, like that. So you just need a commute here. Yeah, 1278. Okay, so this is the general solution for part 2. Anything that we want to fix here? Oh, actually, uh, this could be kind of fun. What if, let's see, so we have P, and then we're checking whether, what if we did like 2-row enclose mix? That'll give us a 2-row matrix. And we could say at 1, we do a neg1 transpose, which I think, nope, the other way. So 1. Like so, this will pull in, so this moves this one space to the right, and then the other one, it shifts it one space to the right, and then the element at the end comes in at the beginning. And now we can do an equal reduce, right? And then use that to filter P. Does this give us the same answer? 1253. Sure does. Yeah, this is kind of a neater way to do it. Saves me some characters. I guess here you can also do like catenate on half axis, like that. Although that's longer, so whatever. Although you don't need the mix in this case. I like the first solution. Okay, this is part 1. That's pretty good. Part 2. I really wish that there was an easier way to sort of say, I want to, for this part here, I want to take just give me 2 rows, whatever the length is for the input, rather than having to do this, like calculate the length and divide it by 2. Anyway, is there an easier way to do that? No, I don't think so. I think you have to do this. Yeah, and then you assign, because using slash as a selection operator inside a train is kind of a pain. One take gets you the first row. Yeah, although we could, actually I can just sum reduce PT here. Reduce first, and then that gets rid of the obligation to multiply. I'm pretty sure anyway. Yeah, 1278. That's a little bit nicer. Yeah. Yeah, I think this is fine for part 2. Okay, yeah, we'll call that our problem 1 solution. Only save file to disk. I still have not, even after a year of using RIDE, figured out just how to save the file to disk without that dialog box popping up. That's kind of whatever. I have a friend that's asking what you making. I'm making nothing in terms of actual productivity. I'm not making anything. I'm just solving puzzles as a warm up to a competition, no less. Do we have anyone? No one's on chat. All right, whatever. All right, problem 2. Glowing humanoid shape yells in your direction. You there. Your state appears to be idle. Calculate the spreadsheet's checksum. For each row, determine the difference between the largest value and the smallest value. Checksum is the sum of all these differences. Oh, all right. Well, this is going to be easy. Pget 2017 2. What do we got? Oof. Those are tabs, huh? Okay. Well, so for each, actually, I'm gonna make this a function. We have to parse out the digits. W jot. You don't need a jot, so this is gonna be membership, like so. Yeah, and then for each one of those, you want to execute them so we get digits. Great. This is gonna be our actual P. And then for each, we want, what is this? The maximum minus the minimum. And then we sum it. Is that the problem? Yeah, apparently yes. 5376. Okay, great. Part 2. Evenly divisible values in the spreadsheet. In the first row, the only two numbers that evenly divide are 8 and 2. The result of this division is 4. I see. Interesting. Okay. What do we got for P? All right, so let's test something here. So evenly divisible is going to be outer product remainder. Zeros along the diagonal. 0 equals. There's a 1 here. There's only 1. Okay, great. So where? And then if it's not going to be along the diagonal, then the indices aren't going to match. So we can call this PT, and then for each not equal reduce. Yeah, that just gives us the 1, and then PT 13.9 take. Wait. Oh, right. Okay, so then we index this. Let's just put this in a function. Omega here. We index that into W, right? And then evenly divides into 31. Right? Okay. Now let's do this for each P. Sum that, 267. Yeah, okay. Great. This is going pretty well. Okay. Well, Tuda dialog does not exist. Do you want to create it? Sure do. All right, so this is going to be same deal. This is going to be nget 2.text in 2.text1 take, right? There's multiple rows, and then what was my parsing? Yeah, like this. It's 2 eaches. It's a little bit gross, but whatever, it's fine. Part one is very easy. So part one is we're just saying for each one of these rows, and if I look at P and I mix this, oh geez. Wait, they all have an equal number of numbers? Is that right? Oh, that's interesting. I don't know if that's true for all outputs. But that means that we can do things rank 1 rather than a bunch of each. I actually kind of like that. Yeah, let's do that. Just because I like working in large arrays when I can. P assign mix. This is now rank 1. D3, yep. And then for the division part, so for the division part, all we're doing is we're just taking the residue, and then if something evenly divides, it means that the residue is equal to 0 if you divide them. And so we're just taking outer product means that we're taking each number divided by itself. So if I did something like this, I think this will all enclose. Although now I have to split this because I'm operating rank 1. So yeah, so for each row, we're doing this, and you can see there's a 0 here, which means that something evenly divided by something else. But we have to filter out the diagonal because that's, something divided by itself is always going to have a residue of 0. Yeah, and then what are we doing? Then we just say 0 equals, give me all the indices where that's true. Right, and then we filter out where the indices are the same. We index back into W, and then we divide. The only difference here is this is going to be rank 1, but that should still, oh geez, 267. Yeah, that's the right answer. All right, well, great. Part 2. Anything I want to change here? Again, we have to kind of assign to an interim variable when we're using selection. Normally, I would like to use a train for this if I'm just assigning a variable to use it once later. But the selection operator isn't great in trains. Yeah, all right, I think this looks good. Save file to disk, no variable. Alrighty. Let's see, I have some text messages here. Isaac, close your blinds. I don't know. You get a view of my backyard, I guess. Whatever, it's fine. Does it mess up the lighting? All right. Problem 3. Come across an experimental new kind of memory stored in an infinite two-dimensional grid. Each square on the grid is allocated in a spiral pattern. Oh, jeez. I hate these kind of things. How big do I have to make it? Manhattan distance between the location of the data and square 1. From your puzzle input all the way to the access port. Fine. Pget 2017 day 3. Sure. Execute. So I have to generate this grid until we hit that number. And then we have to find the Manhattan distance back to 1. And this is just, yeah, this is a spiral out. So, okay, so we're going to start with a 1, 1, row 1. So it's a matrix. And we're going to run a function on it. And that function is going to be so how many elements do we have currently? It's going to be row W, multiply, reduce, right? This gives us 1 because there's only one element in there. And what I want is iota length W plus, yep. And I'm going to do W concatenate. Then I want to rotate this thing. And this should be a matrix, right? Yeah, 1, 2. Great. Okay, so yeah, like so. Good. If I run this twice, what do I get? 1, 2, 3, 4. Great. If I run it 3 times, yep, it's spiraling out. 1, 2, 3. Good. If I run it 8 times. This looks correct. Okay, so now, how long do I want to run it? I want to run it until our number p appears in alpha. Actually, this can be a train, so this will be p in left tack. It's a big one. 571, 571. Okay, fine. And then what is this? We want, can't use index of because it's a matrix, so we'll use membership 1p. Oh, give me the indices. Yeah. Right, minus reduce, absolute value, take sum. 552. Yes, good. Part 2, square 1 starts with the value 1. Wait, what? Same allocation order. You store the sum of the values in all adjacent squares, including diagonals. Only stores 1. Square 3 has both of the above squares as neighbors and stores the sum of their values 2. I see. Well, this kind of recursive logic is actually going to work pretty well for us. So now we're not doing iota anything because we're not generating numbers anymore. What am I doing? Adjacent numbers, this is going to be right tack, so I want the rightmost column and put a 0 behind, put a 0 in front, and then I want to do a 3 window reduce plus, right? Oh, this is going to give me an error though, syntax error. Oh, yeah, of course. Need W here. Wow. Okay. W cons. But this has to be, so I'm not just adding the rightmost column, I'm adding the elements themselves. So I have to do a plus scan first. And now, geez, yeah, transpose, like so. 1124. Yep. This grid is the product of running it probably about 5 times. 6 times, 7 times, 8 times, something like this. 1, 1, 2, 4, 5, 10, 11, 23, 25. The orientation is different. The orientation is different, but that doesn't matter. Because what is the first value written that is larger than your puzzle input? Great, so add this. Let me just 362, 747, 806. 362, 747, 806. So the square generation looks right. And we want to run this until we want to run this until rallable alpha p p less than inner product or right like this. Ravel this. Call this pt p less than pt and grab the first. Well, actually grab the minimum. 330, 785. Yes, there it is. Okay. Interesting. Okay, well, let's see if I can explain this one. So I kind of just blitzed through that. 3.dialog. I sure do. So again, this is going to be ingit in slash 3.text1. In this case, it's just the one row, I'm pretty sure. And then we just want to execute it, and that's P. Yeah. What was my part 1? Part 1. Was here. Let's just make sure that this still works. 552, it does. So what am I doing here? Okay. Basically, so we're building this spiral grid, right? And my plan for building this is I'm going to recursively build it, and each time that I return it, I'm going to kind of rotate the matrix in one direction. So we start with 1, and I have to do this 1, 1 reshape to tell APL that it's a matrix with one element rather than like a scalar or a vector or whatever. And then all that this is we calculate the number of elements that are in our starting matrix. And we can do that by getting the shape, which I do here. So that's this part right here. I'm just getting the shape of the matrix and then multiply reduce. So this is like columns times rows, tells you how many. You know, if I do like a 6, 6 row iota 36, right? How many elements are here? Well, there's 36, but you would know that if you take the shape of this and then you multiply reduce. So, and then I am taking iota length w. So length is going to be the number of rows for a matrix, and I'm adding that to uh, I'm adding that to the number of elements that are already there. So iota, just gives you a range, and I'm kind of saying, hey, skip past the elements that are already there and give me the next sequence of numbers. So I have my next sequence of numbers. I just catenate omega on it. So this is basically saying, like, take that sequence of numbers and make it the new rightmost column, and then I'm just rotating it. And I rotate with transpose reverse first. So that gives me, the matrix. And then I just kind of, like, you can do this with recursion. I'm doing it with the power operator. And I'm basically saying, hey, run this function until our problem input P appears or is a member of the output generated by this function. Once that's the case, I get the matrix back, which as we saw was quite large. And I say, okay, take all the elements of that matrix, tell me which ones are equal to 1 or our problem inputs, and then give me the indices of those. And I can just do this real quick. So the indices are what we're going to be operating on when we talk about Manhattan distance. And I have to find the index of 1 because I don't, because the matrix could be a variable size, I don't actually know what the index of the center is going to be ahead of time, so I have to find it dynamically. And then for each one of these, I mean, we can also just like mix this. So we're working with a matrix. So we find the difference, right? And then we take the absolute value. So this is the absolute difference. It doesn't, we're just looking for how far apart they are. It doesn't matter if the orientation doesn't matter at all. So it doesn't matter if it's like further left or further down or whatever. And then we can, where was I? Yeah, and then we just sum this. It gives us 552. Yeah. I actually like this with the mix at the end because it saves me one character, I think. Oh, I guess it doesn't. I'm still going to keep it. So that's part 1. And do I want to clean anything up here? This is already pretty nice. I'm using a train for the second part of the power operator. This looks fine. This could conceivably be a train as well if I wanted to get fancy. So I could do like train. Like this maybe. I don't know if this is gonna work. I don't know if you can join operators together like that. And this would be like this. Oh, actually, yeah, and it saves me some characters. So I've explained trains. I have a video called Trains, Tax, and the Power Operator on my YouTube video or on my YouTube account that explains how these work. But basically, trains can be they can be pretty nice to save you some characters instead of the kind of standard function syntax or the define function syntax. And then the rest of this is fine. So yeah, I'll go with that. I'm not like explicitly trying to get these solutions as low as I can in terms of character count. It's just kind of fun to do. So okay, and then for part 2, part 2 was up here, right? Yeah, it still works. 1, 1, row 1. I can't abstract this function out because it's completely different, unfortunately. I can't use it in a train either because I'm kind of doing this windowed reduce extra stuff on top. I think this is fine as is, honestly. Okay, so what am I doing here? Sorry. The explanation is basically like instead of, so if we look at part 2, um, if we look at part 2, rather than adding up, like we're not just kind of incrementally counting up anymore. Now we're just taking the sum, kind of the sum of the elements that have happened already, right? So we start with 1, we generate a 1 because we're just taking like 1 plus 0 or whatever. Now with 2, we have to consider these two elements here, right? With 4, we're considering 2, 1, and 1. With 5, this is now 4 and 1. So things start to get interesting around 23, which is when we have to add up actually 4 elements. So it's 10 plus 1 plus 1 plus 11. So basically what I'm doing is I'm considering the rightmost column in terms of triples, and I'm adding like a 0 on either end, so that like here this 2 I can't consider a triple because there's not 3 elements to consider here, so I just put a 0 there, and then that allows me to say like whatever, it's a triple. Or even this starting 1. This starting 1 I can't consider a triple because there's like we just start with 1, so I put zeros on either ends, and that allows me to consider only triples. But for like the first and the last element in the column, um, those zeros come into play, so I'm actually considering doubles. Or in the case of this 1, it's just one element. So, and that takes care of the rows, but we actually have to consider the numbers that came before in the column that we're adding. So I do a sum scan, which just sort of adds. It's like an incremental addition for all of these numbers. So yeah, same deal as before. We take the column, we add zeros on either end. We're doing a size 3 window sum reduce. We do a sum scan. Like I was saying, we add all the numbers that came before. We append it to our matrix, and then we do the same rotation as before. And then all that we have to do then, like basically we're just running this until our problem input is greater than some element in the matrix. You could also write this as I like how this is written, honestly, but you could also do like you do like P equals alpha where Zilda match domain error now. 0 equals length. That's much larger. Well, whatever. I like this first. So this is just saying like ravel alpha, find where p is less, and then do an OR reduce. This is what's called an inner product. And then we ravel that whole thing, and all the geez, yeah. So we ravel this whole thing, and we just find wherever p is less than, and again we have to do this interim variable assignment because we can't use train for selection operator, and then we just take the minimum. So we want the smallest value that's greater than p, and that gives it to us. So I'm actually pretty happy with part 2. Yeah, I think that's fine. I don't see any way to abstract the function. The idea for the function is the same between part 1 and part 2, but the generation is completely different. So I'm not gonna bother trying to abstract that out. It's fine. We save file to disk for name of variable to save as. Cancel. Thank you. What do we got? Revels in making his code as short and as succinct as possible. I mean, look, man, if there's fewer bytes to your code, there's less room for bugs, right? And it all fits on one string or fits on one screen and fits in your head very nicely. Production APL code doesn't really look like this, by the way. Production APL is more verbose. This is just kind of for fun. Okay. Problem 4. High entropy passphrases. Series of words separated by spaces. Must contain no duplicate words. How many passphrases are valid? Yeah, well, okay. So we'll split these on not equals partition, right? Yep. And then, yeah, this will be P. For each P, what time is it? Coming up on 3. Probably do 1 or 2 more problems. This is just kind of a warm up. For each P, we can do unique length dot unique equals length. Appears more than once. Must contain no duplicate words. Yeah, okay, well, sum this. 477. Yeah, okay. For added security, yet another system policy has been put in place. Now a valid passphrase must contain no 2 words that are anagrams of each other. Ooh. Passphrase is invalid. Okie dokie. Well, an anagram is just the count, the sorted, it's like a frequency chart of the letters in each word, right? So if we have, so if we take one of these strings, Bachber, we can use the key operator, and we just say length, like so. This gives us the count of each letter, and then we can sort it to make sure that they always appear in the same order, right? Okay, so let's do this. P, what we're gonna do is we're gonna do this for each one in W. Rank error. You know, I disagree. Oh yeah, this has to be for each sort. that, right? And then we can do the same thing as before. So unique length dot unique equals length sum 167. Yeah. Okie doke. This is problem 4. Yeah, problem 4. 4 dot dialog. Yes, I do. We actually have some interesting processing going on here. So in get n slash 4.text 1. And then for each one of these, we're splitting on spaces, right? So like this. Yeah. And then the answer for part 1 is just this. And so all that I'm doing, this is not that crazy. I'm just saying for each row in P, we take the unique set, we find the length of it. So this function here, unique, if I, where is it? Yeah, unique, just returns returns the result in its argument, minus any duplicates and in the same order in which they appear in the argument. So we just take the length of the unique set and does it equal the length of the original? And if they're not equal, that means that there was some element that was filtered out by the unique function. If they are equal, then no element appears twice. And then we just take the sum. So that's part 1. Part 2 is a little more interesting. You can see here that I'm using the key function. I talk about key in some of my other videos, but you can use, like, anytime that you want to do grouping, you want to think of using the key operator. And here I'm just taking the letters in each word concatenated with the number of occurrences of that letter. And then I sort the resulting matrix. So like, if I had like AA, BBB, C, and I do this key operator, and this is just the letter concatenated with the length. You can see that we get the counts here. And then to make sure that the order of the letters doesn't matter, I sort them. So now you can see, like, if I put A on the end instead, it doesn't matter. You get the same result. And then I just compare these two result matrices. Actually, the logic is the same as we did for part 1. I'm taking the unique set of those result matrices and then checking the length to see if it's the same as the length of the original argument. Then I sum it. So this is a little bit gross here with 3 eaches. But I'm going to do it anyway because this is actually this omega sort index sort omega is an idiom. It's fast. It's recognized by the dialog interpreter. Yeah, I guess I could put this in a function. Yeah, I guess I will. So function length dot unique equals length. That shortens things. And this should give me the right answers. Yeah, 477, 167. It's pretty short. I'll take it. All right, last one. Maze of twisted trampolines all alike. Start at the first instruction in the list. The goal is to allow the jumps until one leads outside the list. After each jump, the offset of that instruction increases by 1. Change it to a 4 for the next time it is encountered. Before we take any steps, jump with offset 0. That is, don't jump at all. Okay, well, what's our puzzle input look like? Pget 2017-5, I think it's problem 5. This looks right. Again, we're gonna wanna execute. So this gives us the numbers. What are we actually doing? Before we've taken any steps, negative jumps move upward. Uh-huh. Well, I think we can do this recursively. So we'll start with 0, P. We need a counter for this. I can do a power function. No, I can't. Okay. So first off, we're going to increase C by 1. And then we'll say we're index 0. So if 0 0 is greater than equal to alpha, or alpha is greater than length W, then we return C. Otherwise, this is going to start in index 1 because we are index origin 1. So we're going to say the new index is alpha index W, and then we're going to say at the new index unjump plus, right? Before we've taken any steps, jump with offset 0. Jump forward because of the instruction we just modified. This is going to be, oh, wait a minute. I think this is alpha plus here. Okay, so without any recursion or anything crazy, can we just print this, please? That's very strange. Oh, I see. Okay, so this is going to be new index alpha index W. Um, this is just alpha, right? Yep, perfect. And we're going to recurse on that along with alpha plus new index. It's probably it's probably an oh, that actually worked. 358, 310. Close. Very close. Why am I off by one? I'm off by one because this increment of C should happen after I evaluate the base case. Yeah. 358, 309. Okay, great. And then part two, now the jumps are even stranger. After each jump, if the offset was 3 or more, instead decrease it by 1. Otherwise, increase it by 1 as before. Um, this kind of conditional stuff is very unpleasant. Well, the fastest way I can do this is if I just say W index ni 3 less than or equal to, right, is 3 or more. Then we recurse just like this, except this is going to be a neg1. Interesting. Really? No, that's right. This is alpha, not new index. It's taking a while. Probably some part two of advent of code. Now that we're starting to get up there to like problem 5, there's usually like you can brute force it, but there's usually some like clever solution you can do to really speed up your solution time. This is brute forcing is kind of fun though because okay, so I have a CPU fan that's like slightly out of alignment. So, oh, there we go. And when you brute force, it spins up a ton, so it sounds like, you know, uh, sounds like something is really happening there, you know. 28178 Yeah, that's correct. Ah, so those are the solutions I'm not super happy about, like the elegance of these. But let's see if we can fix them. I think it's just the one line. Pretty sure. Yeah. This is part one. How would I even go about fixing this? I don't know, man. Mm. Well, first, okay, so I can kind of explain what I'm doing. So this is one of those problems that's a little bit tricky because it's inherently stateful. Like you have this. This happens with all these like kind of mock assembly code or CPU instructions that we get. 2019 we got a bunch of int code problems. It was the same deal. You had this array of numbers that you had to pass around and modify, and it's not like super amenable to elegant solutions in APL. But so what am I doing? Yeah, basically I'm just we start at the beginning of the list and we look there and we're just incrementing or decrementing, and then as soon as we jump out of bounds, meaning that we would get like an index error, um, then we uh, actually I could do check this out. I could put an error guard here. I think this would work. No, it doesn't. That doesn't work at all. All right, never mind. Um, yeah. So we start at 1. We're starting in IO 1, which means that our arrays are 1 indexed instead of 0. And if we have an error condition, meaning that our index is out of bounds of the array, meaning that 0 is greater than or equal, or our index is greater than the length of the array, then we return the count. And if we made it past that, then we increment the count by 1. We have to kind of store the interim value of our new index because we're about to modify it. So actually, I can save some space here because I'm just using it the one time. Yeah, okay, great. We are creating a copy here and we're modifying it, so it doesn't really matter. And then all that we're doing is we're incrementing at the index, we increment it by 1, and then we recurse with the new array, our new state, and the new index. And we just keep doing that until we find until we hit our failure condition, and then we return C, which is the number of steps. So, part 1. Part 2 is like the same type of deal, but now we have this very ugly conditional. Ah, geez. I could index. Yeah, so check this out. So this is, we have a function here plus, what is this? If W index alpha 3 less than or equal to, and we use that to index, we do 1 plus because we're 1 indexed, and we index into, so this is going to be 0 most of the time, and if it's 0, we do 1. Otherwise, we do this. And Oh, no, but now I'm in a function, so I don't have these names available. Alpha, omega. Annoying. I'm just gonna put it here, call it a day. More than 80 columns though. Oh, this is so ugly. Um, oh, I don't need it. I can calculate the value and then I can jot it, so. Yeah, same as before. This is alpha index W, or W index alpha. 3, 1 plus, 1 neg 1, like this. And then I just jot that with plus, and that'll work. And I just recurse with this on alpha omega. Then I can get rid of this, and get rid of this entire branch. 9? Did I get these backwards? Yes, I did. Okay, well, I mean, that's considerably shorter. The performance is kind of a problem. Cannot edit in read-only editor. It's gotta finish first. I mean, I guess I'll let it run just to make sure that I get the same answer. I do not get the same answer. Gross. It's close though. That's the weird thing. It's close. Hmm. Oh, whatever. I'm gonna call it a day. I might patch this up later. Oh, geez. Get out of here, C. Yeah. All right. So I think that is going to be it for today. I hope this was an interesting test run. I may do some more of these to run through some more problems. I'm going to post a recording of this to my YouTube video, and I'll kind of update my Twitch profile so that I have links there, and then to my GitHub, where I will be uploading all the code that you've seen today, and I'm going to start posting solutions to um, the problems that we worked through. So it'll be like 2017 solutions, 2018 solutions, etc. But yeah, for now, I hope that this was at least halfway interesting. And yeah, we'll be back. I think I'm going to be back maybe like Thursday evening. That's Thanksgiving evening for those of us in the US. I at least have a long weekend. So yeah, I think it'll be a fun thing to do with that extra time. So, all right. Well, thanks for watching, and we'll see you next time.